As we continue our review of graphing polar functions, last time we dealt with plotting points and transforming polar equations into Cartesian. Now we're going to go Cartesian to polar. We know that x equals r cosine theta, so x squared would be r squared cosine squared of theta equals 3. Y is r sine theta. We're going to solve for r, and we have it on each side, so let's divide one of them out. And we get 3 sine theta there. Divide by the cosine squared, so we'll have 3 sine theta over cosine squared theta. Or you can rewrite it as 3 sine over cosine tangent theta times 1 over cosine secant theta. On the next one, we recognize this is a circle. In addition to our x and y equations, we also have x squared plus y squared equals r squared, so let's multiply this thing out. So we get x squared plus y squared minus 8y plus 16 equals 9. And that's nice because we have here our x squared plus y squared. So we'll get r squared minus 8r sine theta plus 7 equals 0. Now you want to recognize this is an equation in terms, a quadratic equation in terms of r. So we have r squared, we have r. The coefficient here is going to be negative 8 sine theta. So we're going to use the quadratic formula in order to solve for this. So we'll get r equals negative b 8 sine theta plus or minus square root of 64 sine squared theta minus 4 times 1 times 7. I'm just going to emphasize that right now. It is a little bit more complicated than what you're normally dealing with. We can see we can factor out a 4 there, so let's go ahead and do that. So we'll have 8 sine theta plus or minus square root of 4, and then we'll still have 16 sine squared theta minus 7, all divided by 2. And then now we can do that dividing by 2, so we'll have 4 sine theta plus or minus square root of 4 is gone, 16 sine squared theta minus 1. Now we have solved that equation for r, and that's it. Let's look at the next question. Last class we also dealt with some simple equations that we are graphing, and this time we have theta equals a, like we did before. If theta is a fixed number, r can be anything at all. It's not mentioned at all, so that means we are dealing with a line, or in general they are lines. So then when we go ahead and graph this, we're going to come down to negative pi over 3, and then we're going to graph this line since r can be anything. So let's go ahead and do that. So we have our line. It's going infinitely in all directions, and that's it for there. So then we look at the next one, and this time we have r equals a, so r is a fixed value, but theta can be anything. So what's that going to give us? That's right, it's going to give us circles. So then when we're doing this, if we start with 0, then r is going to be a negative 2, so it's over here. And as theta gets bigger, since we're at the negative, we're actually starting in the bottom half, but it's not going to make any difference at all because theta can be anything, and that is my best attempt at a circle. Yes, I know it is sad, but let's go on. Let's move our page. So now we're going to graph equations of the form r equals a cosine 1 plus cosine theta plus or minus, or r equals a 1 plus or minus sine theta. And do you remember what that is? It's a cardioid. So then before you get, until you know it, what we're going to do is just make a table of values. What we want to do are pick convenient values of theta so that we can compute these easily. Of all of our unit circle values in the first quadrant, which is the easiest, nicest value for sine? That's going to be at pi over 6 because sine of pi over 6 is 1/2. So once we have that, it says we know what in each quadrant it'll be, so we'll have 5 pi over 6, 7 pi over 6, and 11 pi over 6. And at this point, you just plug in the values. So we plug in 0, sine of 0 is 0, so we get 2. Then we have pi over 6 is 1/2, so 1 minus a half is a half times 2 is 1. and then we get 0 for pi over 2, 5 pi over 6 by symmetry. In the first and second quadrant, sign is positive, and this is typical what happens either for sine or cosine. If you know what quadrants you are, you can fill in those ones quickly. So then on this time, 7 pi over 6 is going to be negative 1/2. 1 minus negative half is 3/2 times 2 is 3. So then this time we're adding each time. And then 3 pi over 2 would be negative 1. No, 2 pi would be 0, so that would just give us 2. All right, so now we just go ahead and plot all these points. At 0, it is 2. At pi over 6, it's 1. And then 0. And then we have our symmetry at 5 pi over 6. And then at pi, it's 2. At 7 pi over 6, it's going to be at 3. Down at 3 pi over 2 is 4. And then again, our symmetry. And the 2 pi is going to give us the same thing as there. So at this point, you just do the best job you can to connect those in a curve, and I'm going to do that. And our graph looks like that. I had to pause and just graph it because it takes me 5 minutes to graph using this technology. All right, this next one, I'm going to skip that for right now. You can go ahead and do the exact same thing. Take a look at it and see what happens. Before we answer these questions, let's go ahead and do number 7, then we'll come back and deal with it. So we have here r equals 2 minus cosine theta. Again, we want to pick convenient values. What's the easiest value between 0 and pi over 2? That would be the 1 over 3. And so we want all of those with the same thing with 3 in the denominator. So we have 2 pi over 3, 4 pi over 3, and 5 pi over 3. And at this point, just plug the things in. So you plug in 0, you get 2 minus 3, so you get negative 1. Pi over 3 will give us 1/2. And then at pi, gives us 2. 2 pi over 3. It's going to be adding this time, 3.5. We'll add it again. This is by our symmetry. This will also give us 3.5. And then 2. And then at 5 pi over 3 is going to be the same as pi over 3, so 1/2. 2 pi is the same as 0. So let's go ahead and plot those points and try to make a nice smooth curve with it. All right, and then we have this lovely graph. So this thing has this inner loop. Now, what are these things called? These are called limaçons, and the way you spell it is L-I-M-A-C, but there's that little symbol at the bottom. So now, when we're looking at this, if we say A plus or minus B cosine, if B is greater than A, that means you will both add and subtract the result. You're going to have both positive and negative, and that negative is what's causing this inner loop. So it says there is an inner loop. If absolute value of A is greater than B, that means this B cosine can never make it bigger than A, so that means it's always going to be positive. There is no loop. All right, what I'd like to do at this point is kind of pause in terms of taking our notes, and I want you to play around with the website. So go ahead and go to my website, go to the Desmos activity, and play around with it. I made all these equations up. When you go there, you'll be able to see the whole screen. Do that, play around with it, get a feel for what's going on with this, then come back. But it's important that you do this. Don't just say, oh, I want to go get the notes done with, but go and play with it before I go over the rest of it. All right, now that we're back. So hopefully you could see by looking at these things what's going to be happening here. And the rest of this stuff, we can use Desmos to do it. You're going to need to be able to recognize and deal with this stuff as we're going on, because right now we're just reviewing old material, but we're going to be applying calculus to these things. When you see this number 8, I'm not going to graph it, but you can see that it's 3 plus 2 cosine theta. 3 is bigger than the 2, so it won't have any negative values, so it won't have a loop. All right, let's take a look at this next one. Go ahead and plot these in, and you get that a leafed rose is what this is called. If n is odd, there are n loops in the rows, or n leaves. If n is even, there are 2n loops, or 2n leaves. All right, number 9. We have here a 3 cosine 2 theta. We see the 2 theta, so that means we're going to have 2n loops, so we'll have 4 loops on this thing. The loops will occur when cosine gets to its highest or lowest values, in this case plus or minus 1. So where is that going to occur? At 0 plus pi n. So if we have, then we have half of that because of our scale change of 2. So they're going to occur at, let's see, we're going to go out to a max of 3. And then if we plug in pi over 2, we'll get a negative 3. And then at pi will be 2 pi. And so we'll have it at 3, and then we'll come up there. So basically, we're looking at pi over 2 will get our max values. Now, when you're trying to get a decent sketch of this thing, what we want to do is also realize where is this thing going to be 0. So cosine of theta, or 2 theta, equals 0 when 2 theta equals what? Pi over 2 plus pi n. So theta is pi over 4 plus pi over 2n. So what this is going to tell us is, well, I'm going to focus on this first one. We're going to have a, let's see, a line, kind of an imaginary line here at pi over 4, and I'm going to do negative pi over 4. And you can kind of think of that as our guideline to stay within, because we're not going to, instead of plotting a whole bunch of points, we're just going to try to get one and get a sketch in there. We can plug in, you know, a value like pi over 6 or pi over 12 and see what happens to it. But basically we're looking at this leaf, and it's going to be coming in and it just keeps on going around. And our graph has to be completely kind of within that. Now, is mine great? No, it's a little warped here, but I just wanted to show you actually me doing it. Using this tablet is rather challenging to draw a decent graph. All right, let's do the next one. 4 sine of 3. Since this is odd, there's going to be 3 loops. Our max value is going to be at 4. And where is that going to occur this time? Well, again, let's look at where it's bounded in between. It's going to be bounded where sine of 3 theta equals 0. So in other words, 3 theta is going to equal 0 plus pi n. So it's going to be 0 plus pi over 3 n. So that means we're going to be looking at a value here and there, that this loops will be completely inside. The max will end up occurring at the, basically the middle of there. So we're going to be looking at pi over 6, and then between 2 pi over 3 and pi, we'll have a max there, and then we'll have another one here. And again, look at these spokes. These are all 2 pi over 3 different, or 120 degrees. And then just try to draw a decent sketch here. Try to stay within that boundary there, and then once you've done that, then it's just a matter of kind of continuing the rest of these. So I kind of come down, Again, that was a little challenging. I'm going to stop it and then I'll graph it there. That's not half bad. I'll skip this number 11. You can graph it when you see there. How many loops are we going to have? It's just going to have one. Basically, that's a circle. What's different about it is the center of the circle has been changed, and we did some of those equations last time. When you look at the next one, we're going to see if we have a theta, this time the angle is constantly changing as you're going out. This is known as a spiral of Archimedes. And so this is a bit challenging. You can plot it right now on Desmos. Just do r equals theta. So for every value that you're going out, you're just saying what is that the theta value. So for example, I'm at pi over 2, that's going to be about 1.5, and at pi over 3, it's basically 1 slightly more, and you just keep on going out. At pi is going to be at 3.1-ish, and then at 3 pi over 2, we're getting at 4.7, 2, 3, 4. And then when we get to 2 pi, we get out to 6.3, so it's going to be slightly more. And then you're going to just do the best you can, trying to connect those. And if I was doing this on paper, I'd stop that, but that is it there. So if we look at this next one, again, you're doing the exact same thing, except that negative means you're not going in the same direction. You're not going that positive. You're going to be starting in the negative direction. So go ahead and you can take a look at that on Desmos, and I'll graph it. And you get a graph that looks like that. And our last one, and I think this was the last part of that exploration I made on Desmos, we have r squared equals a cosine 2 theta, or r squared equals a sine 2 theta. This is called a lemniscate. Lemniscate. All right, let's take a look. You can make a table of values. If we solve for this thing, we're going to get r equals plus or minus 3 times the square root of cosine of 2 theta. So when I would look at this, I'm going to say, all right, we want cosine of 2 theta to be greater than or equal to 0. So basically we need to say, what are these values? It gives us a chance we can review our number line here. We are going to say, solve this for cosine of 2 theta equals 0. That's 2 theta equals pi over 2 plus pi n. So then theta equals pi over 4 plus pi over 2n. So if we're looking at a number line here, we're going to say, I'm going to go at negative pi over 4, pi over 2, because we're not restricted between, pi over 4, we're not restricted between 0 and pi, 2 pi, 3 pi over 4, 5 pi over 4, 7 pi over 4, and that'll end up being sufficient for what we need. Between negative pi over 4 and pi over 4, that basically you could plug in a number. If you're not sure, this is positive, so it's going to alternate every single time. So then what do we want? We want those values that'll give us a positive. We're going to look at negative pi over 4 to pi over 4. And so what that does is it gives us an interval, and this interval that we're going to need will give us, all of it will be a length of pi over 2. So if we plug in just a couple of values, again, we want to use kind of some nice ones. We'll have theta. If we plug in 0, well, that's easy. We're going to just get plus or minus 3. And if we plug in pi over 6 plus or minus, given that it's an even function, we'll get plus or minus 3 times the square root of 1/2. Square root of 1/2, you know that's just like sine of pi over 4. Then that's going to give us 0.707, so this thing is going to be approximately equal to plus or minus 2.1. So then when we start to graph this, we'll have 0 gives us 3. And by the way, even though I haven't done it on any of these, you can also change the scale of these and label it what you want. So I can label 3. I haven't been labeling those on these ones, but I really should. So then now I'm just going to plot my 2.1 at pi over 6 and at negative pi over 6. And the lemniscate basically is a loop there. And then we have the negative, the plus or minus, the R values are going to be on the opposite side. So we have 3, negative 3, and then negative 2.1, and then negative 2.1. So it's going to look like that same thing. Now, there you go. Now when you're looking at this, before I talked about the idea of where the values were not defined, or what the boundaries of it, if we look between pi over 4 and 3 pi over 4, it's negative, so we won't have anything, and there's nothing in between there. You don't need to draw those, but there's nothing inside there. A lemniscate has to be of this exact form, and if it's not, you can't do this. You can, in general, you can use your graphing calculators, you can use Desmos, but you need to get a feel for it yourself, because when you're going and you're tested yourself, you won't have the calculators to do. You have to be able to look at it, recognize what's going on, and graph it. If you are not sure, you can always plot points, but realistically, when you're having a test, you don't have enough time to plot a whole bunch of points. And that is it for this lesson.